Hello and welcome back. So finally, after a long break, we are starting the second playlist for International Edexcel Physics. Um, this time we'll start with further mechanics, so Unit 4, and a few changes this time. I'll be making long videos, so one video will cover almost one chapter. And because last time I got few suggestions and comments, and people wanted me to make long videos instead of short videos. So I think this is also good because you'll just have to watch one video before your maybe end of unit test, and it will give you I think if not 100%, maybe just at least 80%, 80-90% of the main understanding that you need to understand this topic. So for this video, this is the outline. We'll start with Newton's second law and momentum, impulse, conservation of momentum, collisions, elastic, inelastic, and energy momentum relationship. And as usual, this will be a very fast-paced course. I will not go into the details. Mostly, I will focus on problem-solving techniques and problem-solving kind of tricks that you can use to answer questions, because equations, you can always look equations in the equation sheet. The main problem is problem solving kind of mindset, right? How you organize your thoughts, how you understand the question. So again, if you have been following this channel, you know how we solve questions, so that will remain the same. Okay, we'll start with this one, and this one is related to Newton's second law and momentum. So the relationship between Newton's second law and momentum. I'll quickly write the equation. Newton's second law in terms of momentum is that force is equal to rate of change of momentum. Where does this come from? We know that F equals ma. A can be written as change of velocity over time. And this m delta v, this is change in momentum, right? Change in momentum is mass times change in velocity. So if you substitute this delta p for this thing here, you get this equation. Now, where does this equation come from? It's not that important. What's important is that you know how to use this equation. What this equation means is that if you have some external force acting on your system, then the momentum of the system will change, right? In other words, if the momentum of the system is not changing, it means there is no external force acting on the system. Or you can also look at it in this way, that if there is no external force acting on your system, then the rate of change of momentum will be zero, which means the momentum will be conserved, right? For the system, the momentum will be conserved. Okay, how do we use this equation? We always write this delta p as final momentum minus initial momentum. That's what it means. Change in momentum over time gives you force. Now, to solve this question, it says which of the following expression gives the average force on the wall during the collision. Now, if you just try to substitute this thing, mv f final minus mv initial, factor out m, you will see that you will most probably select the wrong answer. And the reason is because now when I draw the diagram, you will see why you will get the wrong answer if you just plug all of these things here without imagining what is happening. So momentum, remember, is a vector quantity. So this ball is moving towards the wall. It has some initial momentum pointing to the right. And when it reflects from the wall, this is the final momentum. As you can see, final momentum is pointing in the opposite direction. So if this direction is positive, then this must be negative, because momentum is a vector quantity. So you have to be careful which direction you call positive and which one you call negative. Now, considering this change in direction, if you substitute it here, so force will be minus pf, because it's pointing to the left, minus pi. This minus is from the equation. Pi is plus, and divide by t. And now you can just substitute mvf minus mvi and factor out m. So it will be vf minus vi divided by, minus vf minus vi divided by t. And now if you look at the options, so you will see that we don't have this option in which both of these are negative, because this is the change in momentum of the ball. So that will be the force exerted on the ball. the force that the ball will exert on the wall will be exactly opposite of this, which means there will be a negative sign. So if you multiply this again with the negative sign, so both of these, final velocity and initial velocity, will become positive, and that's our option A. Now, I've tried this question with my students, and most of the students selected C, and they were confused between A and C. Some got A as the right answer, but they couldn't explain why A is correct. So this is the tips that I want to share with you, how you can solve questions. What are the different ways to confirm your answer? Always have a mental picture of the problem, what is happening. Make sure that you are taking into account the direction of vectors. And second tip for this question that I can share is elimination. So you can see we have 2t here. So that doesn't make any sense. You can just eliminate option B and D. So even then, if you have to take a guess between A and C, you will have more 50-50 chance instead of choosing 33% from 4 option. Okay, next is what is the unit of impulse? Now, what is impulse? We'll start with the same equation, F equals rate of change of momentum. And now what we do is we multiply this time on the other side. So change in momentum will be equal to F times T. Now, usually we call this change in momentum, but there are some cases when this change of momentum is so fast that we have to change the name of this quantity, delta P, we call it impulse. So the condition between the main difference between change of momentum and impulse is that this time, the interaction time is very small for impulse. So for example, imagine a baseball bat hitting a ball. The interaction between these two is very small when you hit a ball with the bat. So the contact time is so small and a huge force is delivered in this small time. So then we call it impulse. Usually we write it with J. So change in momentum and impulse, they have the same units. The only difference is when you, in which case you have to apply these two, whether you're calculating impulse or change in momentum depends on the problem. If there is a sudden change in momentum, make sure that you always use impulse. Also in this force will not be constant. So when the ball interacts with the bat, the force peaks, it increases and then falls, right, between this interaction time. So what we do is we usually take this average force between this time, and then we multiply it by the time and we get impulse. So the units will be just Newton second. Newton is for force and times second for time. So it's option C. The next question is a car travels along a straight horizontal road. A drag force of this acts for 15 seconds. Which of the following is the change in momentum of the car due to the drag force? Again, very simple. So change in momentum will be just F multiplied by the time for which the force acts, which is 150 times 15. So that will give you 2,250 kilograms meter per second. This is also the unit of change of momentum. So it is option C. Now these next questions, now we are starting this topic, conservation of momentum. Conservation of momentum is very simple. You just have to remember that momentum is a vector, first of all. Second thing, just like if you remember our last playlist, we solved projectile motion. And in projectile motion problems, we used to deal with x, motion in the x direction and motion in the y direction. We used to solve these equations independently. So just like that, because momentum is also a vector quantity, you have to apply conservation of momentum in x direction separately and in y direction separately. You cannot mix the two equations. I've seen so many students writing m1 v1 equals m2 v2, but they don't know in which axis they are writing that equation. And most of the time they mix the two axes. So in the equation for x, they will be writing the momentum in the y direction for the final picture. Make sure you always solve x and y separately, okay? So in this problem, we have two stones and there is a collision between them. And after the collision, they move like this. This is the final picture. This is the initial picture. Now, the first question is, show that velocity v in this diagram, so they're talking about this velocity, is 1.3 meters per second. This is, now you could do, for example, m1 v1 plus m2 v2, but like I said, you have to stop and think, what are you trying to solve for, right? So maybe you can save a lot of time if you just analyze the problem. Maybe you will always, you can save some steps. There are some steps you don't have to do. For example, if you just start solving in the x-axis, momentum conservation in the x-axis, and you write that total initial momentum m1 v1x plus m2 v2x should be equal to m1 v1 final plus m2 v2 final. This is initial. Then this is something extra. We don't need this. If you look at the problem, you can see that initially we don't have a momentum in the y direction, right? We only have momentum in the x direction. This one is not moving at all. So there is just one object moving and momentum is in the x direction. Now, in the final case, we do have momentum in the y direction. So the velocity is pointing in this direction. And if you resolve this in terms of components, you will see that we have this component pointing up, and we have this component for the second vector pointing down. So here's what's going on. We started with zero momentum in the y direction initially, and in the final case, we have momentum pointing in the opposite direction. And we also know that initial total momentum should be equal to final total momentum in x direction and also in y direction. So instead of solving it for x direction, we can just solve the momentum conservation equation in the y direction, because total initial momentum in the y direction, we know that it should be equal to total final momentum, but the total initial momentum in the y direction is just zero. So our equation is very simple. We just have to write this equation, final momentum, but remember, again, momentum is a vector quantity. So this one is pointing up, this one is pointing down. So there will be a relative negative sign between these. So for momentum of the first stone, I can write m1 v1, and this is the opposite side of this triangle. This is the angle theta. So the opposite sign will be sine of theta. So it will be v1 sine of theta. And then minus, remember, not plus, but minus, because this one is pointing down, m2 v2 and sine of 30 degrees. This one is 50. And I think mass of the stone is the same. So this one is 50. And this on this side we have 0. So you see v1 is 0.87. m1 and m2, each stone has the same mass. So if you rearrange this equation, let's take this thing to the other side, and you will see that mass m1 and m2 will cancel because they are just equal. And then we have to rearrange for v2, this v, right? So our final equation will look something like this. v2 equals v1 sine theta divided by, or sorry, sine 50 divided by sine 30. And that's it. This is our final answer. And if you substitute all the numbers, you will see that the answer is 1.3 meters per second, just like they wanted you to show that this is 1.3 meters per second. Okay, the next question is, deduce whether the collision was elastic or inelastic. Your answer should include a calculation. Now, remember that for elastic or inelastic, the deciding factor is kinetic energy. So if the kinetic energy is conserved, which means total initial kinetic energy is equal to total final kinetic energy, then the collision is elastic. If it is not conserved, then it is not elastic, right? So let's calculate the total initial kinetic energy. It will be just mass of this stone times velocity of this stone squared and times 1/2. So total initial kinetic energy is 1/2 m1 v1 squared, and plus kinetic energy of the second stone, but we know that second stone is at rest, so it will be just 0. And the total final kinetic energy will be, now here you have to understand that kinetic energy or any energy is a scalar quantity. It is not a vector. So you don't have to worry about the angle or the direction x or y axis. That's just for momentum. For kinetic energy, you can just write m1 v1 final square plus 1/2 m2 v2 final square. And again, we can factor out 1/2 m, and this will be v1 final square plus v2 final square. Again, there will be no negative sign because, like I said, it's not a vector quantity, so it doesn't matter what is the direction of kinetic energy, even if it is below the x-axis. It's a scalar number, so we have to add both of these kinetic energies in the final case. And if you solve this, you will see that this one gives you about 27 and this one gives you about 24 joules, which means the energy initial and kinetic energy final is not the same, which means the collision is not elastic, it is inelastic. Okay, next I have here another similar question. So if you understood the first one, you should stop the video and try to solve this one. But you have to be careful. This one is not as simple as this one because as you will see here, we didn't need the x direction equation, but in this question, you will need both x and y equations. Let's see why do we need two equations. So the question is, show that the momentum of the proton after the collision is about this much at an angle this, where theta is about 20 degrees. So we have to prove that the momentum of this thing final is this number here, 5 times 10 to the negative 20 Newton seconds at some angle. So let's write our equations. Let's try to do it the same way. So we can write the y equation because initially you can see we have no momentum in the y direction. It's just x. So in the final case, the momentum should be conserved. It means these two momentums should be equal. So if I write an equation for this one, let's say this is P alpha final, and this is P of the proton final. So this guy right here will be P alpha final times sine of 10.2 degrees. And this one, because it's in the opposite direction, so again, we are dealing with vectors, it will be momentum of proton final times sine of theta, and this should be equal to 0 because we don't have any momentum in the y direction initially, right? Now, the problem here is that although we know the momentum of alpha particle after the collision, so we know this thing, this is given, but this thing, P of the proton final and this angle final, this is unknown, both of these. Remember that you cannot use this angle, just use this angle and prove that final momentum is this much. You have to show both of these things, that the momentum is this and the angle is this. So whenever you have this type of problem that you have just one equation and you have two unknowns in that equation, so that tells you that you need to find another equation for the system, right? So remember this thing, whenever you have one equation with two unknowns, always think different ways of writing one more equation for the system. Let's see what other equation can we write. Remember, this is our equation in the y-axis for the momentum conservation. So we can get another equation by writing momentum conservation in x-axis, and it will be momentum initial should be equal to total momentum final, both in the x directions. So initially we have this momentum. This one is at rest, so there is no momentum for the second particle. It's just momentum of alpha. So let's just write P alpha. And since all of it is in the x direction, we don't have to write cosine theta or anything. It's just all in the x direction. And this should be equal to final momentum in the x direction. Now the final momentum is at this angle, right? This is the final momentum of these two particles. These vectors, momentum vectors, will have y components, which are these ones, and they will also have x components, which are these. X components will both point in the same direction, as you can see. Let's say this red vector is the x component of the final momentum of alpha particle, and this green vector is the final momentum of the proton, x component of the proton. So I can write this as P alpha final cosine theta, and plus, this time it will be plus, not minus, because they are both pointing in the same direction. And it will be momentum of the proton final, and again cosine of theta. Now remember that this theta is known. This is 10.2 degrees, and this momentum is also given here, 8.06. So this is known, this is also known, and P alpha, this is also given. And the only two unknowns in this equation are again PF for the proton and theta for the proton. But now we have two equations and two unknowns. So let's call this one 1 and this is 2. So we can easily solve this, right? By now, if you don't know how to solve simultaneous equations for the unknowns, you should go back and watch the first playlist, but I'm sure you know how to do it. Yeah, if you still have any questions, you can ask in the comments, and maybe I'll explain it in the next video. I'll solve it explicitly. The next question is, deduce whether the collision was elastic and mass of the alpha particle is given. Now for this question, this is actually, now we are doing this topic, energy momentum relationship. So there are two ways of solving this question. First of all, the main idea is that the kinetic energy initial, total kinetic energy initial, should be equal to total kinetic energy final. But the problem is that the kinetic energy for anything is 1/2 mv square. But we are given momentum in this question, right? We know what the momentum is. So one way of solving it is to first write momentum equals to mass times velocity, and then find the velocity first by doing momentum divided by mass of the particle. Then you'll have velocity, and then substitute it here and solve this equation. But if you use another relation, which is the relationship between energy and momentum, and the relationship is very simple. So if you write the equation for kinetic energy, which is just 1/2 mv square, remember that momentum can be written as mass times velocity. So you see, if I write it like this, 1/2 mass times velocity, because this is square, so I can split it. And this m times v is momentum, right? Here. So what I can do is I can write this as 1/2 p times velocity. Now, again, we are not completely, we couldn't completely eliminate v from this equation. We still have one v. So what can we do? To make momentum out of this v, we need to multiply by m. So let's multiply by m, but you know that mathematically this is not allowed. You cannot just multiply m on one side. Either you multiply it on both sides, or another way of doing it is you multiply, but at the same time, you also divide by m. So now this thing is 1, and in math, you can multiply 1 with anything. It's a multiplicative identity, and the definition of multiplicative identity is that you can multiply it with anything without like violating any rules of math. Now, if I write it like this, then I have another momentum, which is this m times v. So I'll have 1/2 p, this one, and then I have another p here. So this will become p square, and this m will remain here in the denominator. So it's p squared divided by m times 1/2. But usually we write it like this, that kinetic energy equals p squared divided by 2m. So this is a useful equation. Why is it useful? It's useful because if you know the momentum of object, but you don't know the velocity, you can just divide it by 2 times mass, and you will get kinetic energy. So kinetic energy is not always 1/2 mv square, because sometimes if you don't know velocity, but let's say you are given the momentum of the system, then you can use this equation to write kinetic energy. So our equation, this one, conservation of kinetic energy, will become that P initial square over 2m. The second particle was at rest, so this will be just the momentum of alpha particle, should be equal to final kinetic energy, which is momentum final of alpha square divided by 2 mass of alpha, plus the momentum square of proton divided by 2 mass of the proton. And this is also a mass of alpha particle. And again, once you take the square of momentum, then it is no longer a vector, it is just a scalar, right? So this whole thing is energy. So you don't have to worry about this plus sign here. This is just from the conservation equation. And that's it. If you solve this equation, and if this is true, then the collision will be elastic. And if this is not true, which means that this is not equal, then collision will be inelastic. The last question is again just a small practice question to use this equation that we just derived. Kinetic energy equals E squared over 2m. So the question is that a non-relativistic particle of mass m has momentum m and kinetic energy k ek. A second non-relativistic particle of mass m over 2 has momentum 2p. Which of the following expression gives the kinetic energy of the second particle? And as you can see, these options are given in terms of the kinetic energy of the first particle. So this is also important question because a lot of students don't know how to solve this type of question. So what you do is you write the equation for the first one. It's just p squared over 2m. Now, kinetic energy of the second particle, let's call it prime, will be momentum of the second particle, let's call it momentum prime squared divided by mass of the second particle will also be m prime. Now, what is the relationship between p prime and p? It is given here that the new momentum is 2 times the old momentum. So p prime is 2p and m prime is m over 2. So we can substitute this here and this will be ek prime equals p prime is 2p. So it will be 2p whole square divided by 2 times m prime. M prime is m over 2. And now if you simplify this, you will get 4p squared divided by 2 and m. Now you see that I did not cancel these two with this one because I want to keep it here, and you will see why. What I can do with this two is that this is division under another division. So it is like a divided by b divided by c. This c is this 2. And if you know fractions, you know that this c should go in the numerator and will be multiplied with a. So it will be multiplied with this 4 here. It will become 8. And I'll have p squared divided by 2m. Now you will understand why I didn't multiply or cancel this 2 with this one. I wanted it to be here so that I can call this whole thing my old kinetic energy. You see, Ek is p squared over 2m. So now finally, kinetic energy prime will be 8 times the kinetic energy that we had for particle 1. And this is option D.